limits involving infinity. Okay, there are two basic ones we're going to be dealing with, or two basic types, and how to work with them. Okay, first one, horizontal asymptotes. Line y equals b is a horizontal asymptote of the graph of the function y equals f of x if either the limit of f of x as x approaches positive infinity is equal to b, or the limit as x approaches negative infinity is b. Okay? So as we get really, really large or really, really small, do we approach a particular value? If we do approach a particular value, that is a horizontal asymptote. Now, horizontal asymptotes don't mean that somewhere in the middle they cross somewhere. Your graph does not have to, your asymptote is not something that the line never crosses. Ever. That's not true. It's that as you get really, really large or really, really small, your graph approaches that line. Okay, it gets close to that. It's an asymptote. Okay, and they do not have to necessarily be the same one in each direction. Or you have to have an asymptote in both directions. You can have one in one direction, one in the other direction, or two separate asymptotes in each direction, depending upon the equation you're dealing with. It all depends upon the equation and what's going on. Okay. Yeah, so it could be to the left or to the right, either one, and you have to check both. Okay, a few years ago, AP threw out a test question that I thought was an absolutely wonderful question, but they threw it out. And I'm really, really mad at them for throwing it out. The question was multiple choice. They gave an equation that said, what are the horizontal asymptotes? And they threw the question out because the majority of people who got a 5 on the test answered the same incorrect answer. And the problem is that it had one asymptote one direction and one asymptote in the other direction. And your choices were, here's your asymptote, here's your asymptote, here's your asymptotes, or none at all. And they answered only in one direction. They did not answer in both directions. Because it was two different asymptotes, one to the right, one to the left. They did not answer that. They answered only to the right. And I thought, well, they deserve to get it wrong. Because you are supposed to check in both directions. And if you don't check in both directions, I will mark you wrong. Okay, I do not agree with them letting that one slide just because the majority of people who did really well on the test got it wrong. I don't care. It's still a good question. They should have gotten it right. They have bad questions. I've seen bad questions on AP tests. That was not a bad question. That was a good question. Okay. Okay, now, we have some examples here. Okay. F of x equals x over the square root of x squared plus 1. And this is a perfect example of left and right asymptotes being different. If you graph it very, 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 very quickly, you see that you have asymptotes. Now, sometimes these asymptotes don't show up so fast. I mean, we've got them by the time we have the 5 and negative 5. You've got a really good idea you've got behavior, asymptotic behavior going on. But in the middle, we got other stuff going on. We don't always have this situation. It may be much farther out before you get to there, but you have to try larger values. Now, graphically, it's easy to see. And if I were to take that graph and zoom way out, to the thousands, it's really easy to be able to see where your asymptotic behavior is. But you do have to understand what's going on here algebraically. So if I put in very large numbers, if I look as I'm going towards infinity, and I put in very, very, very large numbers. Now, I don't have to worry about any domain issues. Because x squared plus 1 will always be at least 1. Right? Never going to have to worry about domain issues on this one. There aren't any issues on that. Okay? But when I put in very, 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 very large numbers, 10,000, 10 million. Okay? If I take 10,000 and square it, does the 1 really matter? It doesn't really matter. It's insignificant at that point. Even if I only put in 100, realistically, I put in 100 squared plus 1. Now, that 1 is really insignificant to what's going on here. But I get even larger. Remember, we're going towards infinity. We're going out to the thousands and the millions and the hundreds of millions and so on and so forth. We're getting really, really big. So as we go along, this 1 becomes irrelevant as we get really, really large. And as I put it in, so the 1 becomes irrelevant, I can ignore it. This is essentially the square root of x squared, right? And what is the square root of x squared? X. What is x over x? 1. As long as x is positive. Because remember, if I take it and square it and square the root, the denominator will always be positive. The numerator is only positive when x is positive, but the denominator will always be positive. So if I end up getting x over x, that's 1. That's why it's asymptotic towards 1. Because as I go really, really large, this becomes irrelevant. This whole thing becomes essentially x. X over x is 1. Okay. If I look at it from the other direction, same idea. If I put in really, really, really small values, and by really small, I don't mean like 0.01. I mean like negative 10 million. That's a whole lot smaller than 0.01, right? Okay. I'd rather have a penny in my bank account than owe $10 million. Okay. So same idea. This 1 becomes irrelevant. It becomes irrelevant. So I have a very large number squared, and then I take the square root. So this becomes essentially x, but not x itself. It becomes the opposite of x because I have a negative. This is always positive, right? This is always positive. So if I put 10 million in here, square it and add 1, and then take the square root, I get basically, if I put negative 10 million in, I get essentially positive 10 million back, right? Because it's going to be positive. My numerator is negative because I'm going towards negative infinity. I'm putting in negative values. That's why it goes towards negative 1. You can tell by the graph. You can also tell algebraically. You can't put a million into a function and evaluate it. Oh, I'm going to plug a million in here and see what I get. You can't do that. Infinity. You can't. And you could put a million in there. I wouldn't want to. Okay, but you can't put infinity in there. Infinity is a concept. It's an idea. It's something we're heading towards. But you can, in your mind, if I'm putting larger and larger and larger values, I mean like millions and millions and millions, huge, giant numbers, what's going on? And that's part of what you're going to have to be doing today. And there are some shortcuts to help you with that. Okay. So we did these properties. There is a new property added on here, though. And this is kind of an important one, number 6. I don't think you got property number 6 last time. The limit of a function to a power is the limit of that function to the power. So, for example, the limit of x squared, the square root of x squared, is the square root of the limit of x squared. What's nice about this, notice how the power is written. It's a rational exponent. We are not going to do a lot of work with radicals and leave them as radicals. You will be taking most of your radicals and converting them over to fractional exponents. We can work with fractional exponents. We will not be able to work with radicals, generally speaking. Okay? So yeah, that's an important one to remember that one. We have that rule. We're going to do a lot of fractional exponents in here. You got to get real comfortable with them. If you're not already, you will be. Okay. So we kind of worked this one out. We talked about this one already. Okay. This one's a little harder though. Okay. If I look at this one, We talked about what happens if it gets close to 0. The limit as x gets to 0 of that is 1. It's essentially 0 over 0, which is 1. If you don't actually hit 0, you can't do that. As I go towards infinity, okay, as I go towards infinity, what's going on here? What is my maximum value of the sine of x? Come on, what's my minimum value? So this is always going to be somewhere between 1 and negative 1. What happens with my denominator, though? If I get 1 over 10 million, it's really, really close to 0, isn't it? Okay. If I get 1 over, 100 million gazillion, it gets basically 0, right? As my denominator gets really, really large, my numerator does not match its growth. So as I get a larger and larger denominator, overall the entire fraction is close to 0. Does it ever actually become 0? Not really, but this is kind of an interesting case. Because as x gets larger, as I put in larger values, what happens to the numerator? It goes between 1 and negative 1. And what does it hit in between? 0. Constantly repeating. Sine is going like this. Constantly. But my denominator is getting large. So what is my graph of that doing? So if I have my x-axis going out, my graph is going like this. Now here's the thing. This is asymptotic behavior. You've always been taught an asymptote is a line where your graph approaches but never touches. This one repeatedly crosses the asymptote. It's kind of like one of those where you zoom in and you get the exact same thing every time. No matter how close you zoom in, it will always look like that when you get out to the ends. It's constantly crossing, but it's narrowing in on it. That is also considered asymptotic behavior because it essentially becomes 0. It does go back and forth, but man, that back and forth is like really tiny at some point, and it essentially becomes the x-axis. So it is asymptotic even though it actually touches. Okay. So this one below. You're going to have to get really good at algebra. I can kind of do the same thing here. And if you look at it, it works exactly the same way. What's going on in my denominator? As I go towards positive infinity, it's growing very quickly, isn't it? As a matter of fact, it's growing even faster than the previous example was. So it's getting even smaller and smaller and smaller. Even faster. So you've got the same thing going on here. So you can, in your mind, reason out what is my limit. Hey, it's 0. Same as the previous one. These two, there isn't much different. This one actually gets smaller faster than that one does. Because when I get out to like 1,000, 1,000 squared is a whole lot bigger than 1,000. When I got out to 10 million, I squared 10 million and I got 10 million. This is really becoming insignificant. Okay, so I have 100 billion and I square 100 billion and I have a billion, 100 billion. 100 billion squared is a whole lot bigger than a billion is. 100 billion, this becomes irrelevant. The larger x gets, this also becomes irrelevant. This grows extremely quickly. Now, there are some other things we could do. This denominator is factorable. I could look at it like this. It's the limit as x approaches infinity of the sine of x over x times 2x plus 1. Oh, there we go. Which equals the limit as x approaches infinity of the sine of x over x times 1 over 2x plus 1. And what's this? We already did that one, right? What's that? It's 0. So this one's 0. What is this one going towards? As my denominator, if I put in larger values of x, what does that head towards? 0. It also approaches 0. As my denominator becomes very, very large, 1 over a very large number, essentially becomes, is it actually 0? No, but it approaches 0. The limit of two things multiplied is the limit of two things multiplied is the limit of the first times the limit of the second one. I get 0. So you can look at them algebraically. You can figure out. You can't evaluate it from pointing numbers in. This is one where you have to intuitively go, what's happening when I put in really big numbers? When I put in really big numbers, what's going on? Any questions so far? Yes.
So why is the sine x over x 0 again?
Okay.
Oh, okay.
Any other questions?
Yeah, one more.
Yeah.
Could you figure that out without even like doing algebra?
Well, yeah, you could. The same idea. When we talked about this, what's going on here? This is getting extremely large. What's going on here? Well, that's between 1 and -1.
Yeah.
Yeah, and that's what will happen. Difference is when we get close to 0, this one is much different than the other one. Okay. So, your turn. Here's a hint. Okay, in the interest of time, we will finish this one because we do actually have quite a bit to cover today. We should be able to get through it, but we do have quite a bit. Okay, so that's the limit as x approaches infinity of 5x over x plus the limit as x approaches infinity of sine x over x, and we know that this is 0 from what we've done before. And what is 5x over x? 5. And what is the limit of a constant? It's that constant, it's 5. So our answer is 5. The limit is 5. It approaches 5, not 0. Okay. Very close to the same behavior as before, but yeah. Okay, this is what is going to help you do these kinds of things, and we've already discussed this to a very large extent. End behavior models. The function g is a right end behavior model for f if f of x over the limit as x approaches infinity of f over g is equal to 1. The function g is a left end behavior model for f if the limit as x approaches negative infinity of f of x over g of x is 1. So essentially, for very large values, do I get 1? Is the numerator and the denominator the same, essentially, for very large values? That's my end behavior model. That is the definition of an end behavior model. What an end behavior model is basically saying, hey, when we put in very large values, what does that function essentially look like? When we put in very, very small values, what does that function look like? We've already done some of that. Okay, when you look, remember we had the square root of x squared plus 1? And what do we do? When you get really big, the 1 becomes irrelevant. That's kind of what you're doing with an end behavior model. Okay. So show that X is a right end behavior model for X plus e to the negative X. Here's essentially what you're doing. You use end behavior models to discuss what's going on and to find possibly asymptotes. But it's also to describe what's going on. If I put in very, very, very large values, 1,000,000, 1,000,000,000, 1,000,000,000,000 in for X, what is going on for e to the negative X? And remember, what's happening to this? It's getting really, really small. So small that it is essentially insignificant. So this X, this is my end behavior model, my right end behavior model. EBM, right EBM, right end behavior model. X is my right end behavior model because this becomes essentially zero. It is irrelevant. If you graph this and that, they become the same thing essentially very quickly, as a matter of fact. Very quickly. So I can use X to analyze X plus e to the negative X power for extremely large values. Because they're almost the same thing. When we're talking millions, they're essentially the same thing. You know, 1 over e to the negative, 1 over e to the thousandth, this is basically zero anyways at 1,000. At 100, it's really close to zero. So at 100, this is basically, this is 100. If I put in 100 for X, this is basically 100. 100 plus need to be a little bit. It is basically irrelevant. It's so small compared to what we're actually valuing. Okay? So if I look at this one, same function. And I want to know what's going on as X approaches negative infinity. What is my left end behavior model? As X gets really, 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 really small, what's going on? If I put in negative 10 million, if I put in negative 1 billion, what's going on? No. Because take a look at what's going on. Remember, I have two types of functions here. I have essentially a linear function, and I have an exponential function. And this exponential function grows how much faster? Compare x to x squared, x to x cubed. Which one's going to take overpower quicker? When I start getting to a certain point, and those are only polynomials, when I take like 10, you know, to the x power. So if I put in 1 or 10, if I put in 100 for x, I got 100, I got 10 to the 100th. You tell me which one matters more, 100 or 10 to 100. Which one's going to matter more? Because when I put in negative values, this is actually the equivalent of e to the x. This becomes so huge, so fast, this becomes irrelevant. Is it asymptotic behavior? No. But what it does is say, hey, when I get really, really, really big, I can just talk about that. Or sorry, really, really small, I can just talk about that one. Okay. If you graph x, e to the negative x, and x plus e to the negative x all on the same graph, you'll see exactly what I'm talking about. In the middle, they don't line up anywhere near each other. But when you get really large and really small, they become, you'll see things line up very closely. That's when an end behavior model does.
So if we're asking a question like something else, how would we direct it? Like,
You'd have to say this is an end behavior model. You'd have to identify what it is. It's not, it's an intuitive thing. It's not so much very much a proof. Can you prove that it is? Show that it is? You kind of have to just demonstrate and explain. Usually, if I ask them on the test, I would say, hey, use your end behavior models. What's the end behavior model for this? What's the end behavior model? That's the only type of questions I've ever seen. But where they come in handy, and I think this is what's coming up on the next slide, is using them to find asymptotes. Okay? If I have rational functions, okay, the ratio of the two largest portions of the polynomial is my end behavior model. Okay? So as I approach infinity or negative infinity, if I'm looking for an asymptote, this will tell me whether or not I have an asymptote. My end behavior model, okay. Now I actually want to look at that. That's my end behavior model for that function. Because as x gets big, the plus 1 in my denominator is meaningless. So it's essentially 2x cubed over x squared. And when I simplify this down, what do I get? I get 2x. Okay. As I approach infinity, what does that approach? It approaches infinity. Woo! Popped right in the middle there. So my limit, do I have an asymptote? If I approach infinity, if as x approaches infinity, my limit approaches infinity, do I have an asymptote? No, because what is an asymptote? Is when it approaches a particular value. So my asymptote in this case would be, there is no asymptote. It grows without bound. That's what's going on. It's like a line. What does the end behavior model look like? For that function there, it looks like 2x when you get really large. That's what that graph looks like. It's like 2x. When you get really, it also happens to look like 2x when you get really small, too. And it'll go towards negative infinity. Because that's what end behavior models do. Okay, so if I look at the next one. I look at that. Which is what? What is my end behavior model for that function? 3/4. So if I take the limit as x approaches infinity, oh, no, you don't go there. You go there. It's 3/4. So do I have an asymptote with that one? Yeah, my asymptote's 3/4. Last one. Polynomials are easy. End behavior models for polynomials. Polynomials will be the easiest things you will work in. You'll love seeing polynomials are easy. End behavior models are great. You just take the highest power exponent. Whatever highest power you have for your polynomial, that's your end behavior model. That's what it looks like. So for this one, my end behavior model would be 3/5x, which as I go towards infinity, it heads towards 0, which means I have an asymptote of 0. Okay? We're going to be tight. Questions? Okay. Vertical asymptotes. Vertical asymptotes are nearly, well, the same idea, only instead of heading towards, instead of we take the limit as we head towards infinity, we take the limit towards a particular value. If our limit goes towards infinity, that is an asymptote. That is a vertical asymptote. As x approaches a particular value, if x goes towards, let's say, 2, my limit is infinity, i.e. it grows without bound as I approach a particular value, I have a vertical asymptote. and it's plus or minus infinity, and its x approaches the value a from the left and the right. You have to come at it from both directions unless it doesn't exist on one side or the other at all. Biggest question is, where do I find those values? They're actually very easy to find. About the only place that those values will exist where you have a vertical asymptote. And picture in your mind the kind of graphs that have vertical asymptotes. What happens? You have a denominator that goes towards 0, right? They're undefined because you have a 0 in your denominator. That's everywhere you have a vertical asymptote. It's because the function doesn't exist there. So you have to find out where the function doesn't exist and then evaluate it to see if you have a vertical asymptote or not. You might not. Okay, so consider the function f of x equals 1 over x minus 2. Where might my vertical asymptote exist? Wherever my denominator, x minus 2, is equal to 0. Wherever that function is undefined, it is the only place. Not guaranteed to have a vertical asymptote, but it's where I look for one. Remember, nothing is ever guaranteed to happen at particular places, but they're the only places where they might happen. We're going to be looking for what we will call critical points later on, and critical points are where interesting things can happen. They almost always do, but they don't always be what we want them to be, but something interesting is going on there. I guarantee wherever my denominator is 0, something interesting is happening. Something interesting is going on. We don't know what, but we do know something interesting is going on there. So, something interesting is going on at x equals 2. So what I have to do is I have to take the limit as I go towards 2 from the right and from the left. I look at it from the right. Now, think with me on this one. I'm putting in numbers closer and closer to 2 from the right. So I start at, let's say, 3. Okay. 3 minus 2 is 1. 1 over 1 is 1. Slightly closer to 2, that 2.5. Right? So I get 1 over 1.5, which is 2. What happened? It just doubled in size. 2 1/4. I get 1 over 4, which is 4. 2 1/8, which is now 8. 2 1/16, which is now 16. You see what I'm doing here? As I get closer and closer to 2, what's happening to my number? It's getting larger and larger and larger. That is why it's going towards infinity. The closer this gets to 2, the smaller the denominator gets. The closer to 0 the denominator gets. It's a fraction. 1 over a fraction is the inverse of that fraction, right? So if I have 1 over 1 billion, this is 1 billion. So the closer I get to 2, the larger this gets. That's what's going on here. It's the closer I get to 2, that's going up. That's creating my asymptotic behavior. Doesn't ever actually become 0 because it can't be 0, but it gets really close to that, or it doesn't become 2, but it gets really close to 2. Same thing as I'm putting a number slightly smaller. Problem is slightly smaller means my denominator is negative, the whole thing is negative. That's why it goes towards negative infinity.
Is there ever become a point where the just small distance between the two, consider it retouching?
Okay, good question. Good question. Good question. Mathematically speaking, in absolute terms, no, it will never be the same thing. But if I were an engineer, yes. It's funny. My dad was an engineer. We joked about this. And to a mathematician, pi is the circumference divided by the diameter. It is pi. It is a value of pi. To a physicist, 3.141596. To an engineer, that's about 3. Okay, all depends upon what you're doing. Essentially, it would be 0, and we would treat it at 0. But for a number so large, we wouldn't care. Okay, does that make sense? So we're dealing with things differently in math than I would, let's say, if I were a physics teacher. The math would be the same, but my results might be a little bit different. I'm more exact in here. I want exact values. In there, close enough. Does that make sense? Okay. And who you're working for? You're working for General Motors. Or you're working for NASA. Okay. So, find any vertical asymptotes to the following. First question, where might they happen? Second thing you need to do, go at that number from the left and from the right. In the interest of time, we'll do this one fairly quickly. X cannot equal 0, so that is where I'm going to look for my asymptotes. Okay, so I take the limit as x approaches 0 from the right of 1 over x squared, and that would be positive infinity. And if I do the limit as x approaches 0 from the negative, from the left of x squared, I also get positive infinity because I'm squaring it. So it's always positive. So I have an asymptote at 0, it goes up like this. We've all seen it. Do I have horizontal asymptotes? Yeah, as I go towards infinity, my horizontal asymptotes are 0 in both directions. Okay. And if you remember the graph of this, what does that look like? Looks like that. Makes sense. So there is one more problem. We will not have time to finish. Well, yeah, we won't have time to finish in class. I do want you to do this in your notes. Remind me tomorrow. We'll go over this last problem together. It will not be on the recording, though. Here's a hint. Factor. Factor to look for your asymptotic behavior. Factor, factor, factor. No, just look for the vertical ones on this. Do the vertical ones on this. But there are horizontal ones as well. The horizontal ones are easier to find. Okay. No. No, I hit stop. Oh, I'm sorry, I was looking at getting out at 106. I don't know why. All right. Now, you need to be careful when you do this, because my important points come from my original function, not my simplified function. But I can use my simplified function to do my limits, okay? Because the limit of this function is the same as the limit of this function. They are identical when you graph them, except for one feature. Now, x cannot be 2 or negative 2. Those are my two places I need to worry about. Now, if I take the limit as x approaches 2 of x minus 2 over x squared minus 4, that's the same thing as the limit as x approaches 2 of 1 over x plus 2, which is 1/4. It heads towards a number, and it does it from both sides. I can just substitute it in. I do not have a vertical asymptote at 2. Okay. What I do have there, though, is a hole. I have a hole in my graph at that point because it's undefined at that point. It's a line going with a hole right there. The difference between this, the graph for this, and the graph for that, is the hole at x equals 2. At 1/4. You have the point 2, 1/4, there's a hole there. That's the difference. This graph doesn't have a hole. That one does have a hole at that point. The original function does. So I do not have an asymptote at x equals 2. However, pretty much can guarantee I do have one at x equals negative 2. So I take the limit as x approaches negative 2 from the left of 1 over x plus 2. And that goes towards what? Starting with numbers smaller, so it would be negative, right? So this would be negative infinity, right? Numbers smaller, no, number small, that would be positive infinity, right? 1.9 negative, or sorry, yeah.
Negative.
Yeah. Did I know negative 1 point? Yeah, you're right. I got to stop and think sometimes myself. Negative infinity. The limit as x approaches -2 from the right of 1 over x plus 2 would be positive infinity. Therefore, I have a vertical asymptote at x equals -2. Now, before you run out the door, hang on just a second. Hang on. End behavior models. So if we go back to what we were doing before, the first one, where we had the original function x plus e to the negative x, the right and left end behavior models. Okay, the red one is our original function. If we zoom out, look what happens. Becomes exactly the same to the right, to the left, but only at the ends, not in the middle. That's what end behavior models are about. Okay? Thank you very much. You've been a wonderful audience.